Right, so this is part 3. So how do we know that whether the point, based on stress, whether the point is in this situation or the point is inside the boundary? Okay, so we're going to form the equation of this line over here. Okay, so we're going to form the equation of this line. All right, so the equation of this line, so we know that y-axis is the response, so we can find that stress B will be equal to the ultimate stress U in compression. So this is the gradient, so it's delta y over delta x plus by the response, but the variable stress A is on the x-axis, and the y-intercept is equal to minus stress U compression. So this is a expression. So we're going to divide everything. Okay, so we're going to divide everything by stress, ultimate stress compression. Okay, so UC. So this is stress A over stress UT minus by 1. Okay, so we divide by stress UC. So we just rewrite this. So 1 is equal to stress A over stress UT minus by stress B over by stress UC. Right. So if we look at this expression now, okay, so if stress A over stress ultimate tensile minus stress B over stress ultimate compression, and this is less than 1, okay, structure will not fail. Okay, structure will not fail. And then if stress A over stress ultimate tensile minus stress B over stress ultimate compression is greater than 1, then you're in trouble. Structure will fail. Okay, I'm not done this yet. Okay, I'm not prepared this, but I'm going to do this live. So we're just going to put in some numbers. Okay, so we put in stress UT, just some simple numbers, is equal to 1. Okay, stress UC is equal to 5, for example. Okay, then we have our stress A. Okay, so that's our value. So condition number 1. We have stress A is equal to, for example, stress A is equal to 0.2. Okay, and stress B is equal to 4. Okay, let's say 4.5. Right, so you plug in the value. So 0.2 divide by, so you plug into the divide by 1, right, minus by stress B is 4.5 divide by 5. Okay, so 0.2 divided by 1, 0.2 divided by 0.2 divided by 1. So it's 0.2 minus by 4.5 divided by 5 is equal to minus 0.7. Right? So for this case, structure will not fail. Okay, I do apologize. When it's compression, you have to put in minus. Okay, this is okay. I mean, stress states are magnitude, right? So 0.2, 0.2. So plus by 4.5 divided by 5 is 0. Oh, I do apologize. 0.9. So what do you? So you have to include magnitude. I do have to include. It is a vector. Stress is a vector. Okay, stress is a vector. So down here you treat them as magnitude, right? Because how this is derived, we treat them as a magnitude, right? So this is a gradient, and it's positive shear. We treat them as magnitude. So we realize that this is equal to what? So 0.2. So 0.2 divided by 1. So 4.5 divided by 5 is 0.9. So this is 1.1. So the structure will fail. Okay. So let's go a bit conservative. Let's push this back to, so condition number 2. Right, condition number 2. So stress A is 0.2. Now we reduce stress B to make it 3. Okay, and see what happens. So 0.2 minus 1 divided by minus 0.3 or minus 3. Right, minus 3 divided by 5. So this is a 0.2 plus by, so 3 divided by 5, 0.6. So this is 0.2 plus 0.6 is equal to 0.8. So now we know that our structure will not fail. Okay, so this is how it works. So let me explain it again. Over here it is positive. It's because the gradient over here is positive. So if your ultimate compression, now I know you'll get a negative value, but you have to put in your what? You have to put in your positive value. Except stress B. Okay, so all this, right? All this, these two are vectors. Okay, you have to remember that. Right. So we are going to look at one example. Okay. So the example, we're going to use the simplified Moe circle. Okay, we're going to do. So we're going to look at one example. Okay. So we have, what we are given is the ultimate tensile is 10 times 10 to the power 3 psi. And then we are given that the ultimate compression is minus 30 times 10 to the power 3 psi, right? So we are given Moe circle. Sorry, we are given the element load. Okay. So over here, X and Y. So we are given tensile of 2000 psi, and then we have a compression of 15,000 psi, and then we have a shear of 9,000 psi. Okay, we are given 9,000. So we're going to ask were the material Okay, we are asked with the material. I can't spell material now. Well, the material fail, right, under the loading condition. Okay, based on simplified data simplified moles criteria. So we're going to find, so therefore we have to find what? We have to find what is our stress A and stress B. So our principal stress, okay? So based on plane stress condition. So as I mentioned, plane stress condition where stress Z has to be what? Equal to 0. So we don't know whether it fail or not. So whether is it operating inside this blue shaded region, okay, blue shaded region, or is in the red region. Okay, so that's where we have to find out. So as we don't know where it is, and we have to work this out. We have to discover it. So we are going to we have to construct Mohs circle first to find what? Stress A and stress B. And more important is stress A, stress B in plane. That is the question again. Okay, so now we have to construct proper Mohs circle. So stress Y is 15,000. Okay, so I'm going to quickly sketch out our Mohs circle.